Good morning, everyone. Today we continue with our PoligonSoft free classes. We are now on the third class. In the first class, we studied how to correctly create finite element meshes in the program. In the second class, the previous class, we simulated a simple model using the classic simulation method, the method where we have the mesh of our mold and the mesh of our part available, and all we need to do is adjust the simulation parameters, run the calculation, and then we get the results. Today we will talk about a slightly more complex simulation. It involves the mesh we made in the first class for this part that we see on the screen. A steel sand casting, but since the model itself had very large dimensions, we couldn't generate a mesh with fewer than 500,000 polygons if we had included the mold. Therefore, we only made the mesh of the part itself. And in today's class, we will be learning how, in the PoligonSoft program, using the so-called virtual mold, we can set all the simulation parameters without having a mold. Let's begin. First, as we did last time, I run our master module to enter the main module, the module where all the parameters of our simulation are set. First, let's open our geometry. We select the Salom line here, which corresponds to mesh data. We leave the units in millimeters, click OK, and select our mesh made in the first class, Lesson 2. Alright, done. The dialog appears asking whether to keep the parameters from the previous simulation or load the default parameters. This time we won't load any default parameters. We are learning how to work. We will do everything from scratch. What can I see here? I'll switch to the volume types mode. We see that our volume currently corresponds to the casting volume type, meaning it's a casting. This is obvious because we don't have any other parts, nothing that can be assigned to the mold, so our volume was assigned volume index 1 and is in the casting volume type. As we can see, the model opened in a position that seems incorrect. Why did this happen? Because, as I mentioned earlier, the gravitational force in the PoligonSoft program is directed along the y-coordinate. And if we created our model in a different coordinate system, when we open the model in the program, we will always see these kinds of things. How to correct this error? We switch to the main tab of the program, click Reset Rotations to see the model's current position, and we need to rotate it. In which direction will we do it? Here we can see that upwards we have the green axis, which is the y-axis, and towards us we have the z-axis, and the red axis, which is the x-axis, is directed to the right. We will rotate it several times around the red axis, the x-axis, 1, 2, and 3. Now the model is in the correct position, but we need to fix the orientation. We click the Fix Rotation button. Now, as we can see, the program changed the coordinate system, and the y-axis is now correctly oriented. The model is oriented as the PoligonSoft program needs it. Let's continue. The second thing we need to do is assign the materials. For our casting, we will assign the material exactly as we did in the second class. We simply go to the Project tab, and for the material of our casting, we click the pencil icon and find the necessary material in the database. Today we'll be working with this steel. It's a widely used steel in castings of this type, which I am making, a pressure valve. Click Apply and Close. But now, last time we assigned the mold materials using the volume indices mode, assigning these indices here that corresponded to different volume indices in our model. But in this case, we have only one element with index 1 and nothing else. How can we tell the program that I want this to be inside a sand mold? Let's see. In case the program doesn't find how to explain it, it's a bit non-obvious, but we need to understand because it's very important how this works. First, let's load a heat transfer template. We'll load the template corresponding to sand castings. I'm going to select this one because it contains data for exothermic sleeves. We'll discuss that a bit later in the second part of our class. We now have the template for our heat transfer parameters. The heat transfer parameters are those that correspond to the boundary indices, which is where the heat exchange parameters between different volumes of our model are established. In this case, we only have one, and as we can see, the program automatically assigned the boundary index to our entire model, which by color, if we check here, you'll eventually learn this by heart just by knowing the colors. But I'll show you now. This color corresponds to index 17, which is the heat exchange index between our casting and the environment. This is obviously incorrect. It means that the part is hanging in the air and will cool down by radiation to the environment. First, let's change these boundary indices here. Click the Edit tab and select Boundary Indices. As I said, index 17 is currently assigned to the entire part, so let's select it here. Volume type casting, index 17. Check the box to select it. OK. And the program has selected the entire surface of our part. We are going to tell it that this surface actually exchanges heat, not with the environment, but with a mold. Click Assign Index, and here we select the corresponding index that was loaded from our heat transfer template. It will be index 1 for heat transfer. Okay, now the program knows that all surfaces of our part interact not with the environment, but with a mold, and that they have the heat exchange parameters established on this screen. Since we selected all surfaces, and not one by one, we need to tell the program that the surfaces truly interacting with the environment, which are these two up here, have index 17, the heat exchange with the environment. To select the surfaces, holding down the Control key, we select with the left mouse button the surfaces we are interested in. If we have selected a wrong surface, we can deselect it by clicking the right mouse button. Left selects, right deselects, always while holding the Control button. We now have the necessary surfaces selected. Let's assign index 17 to these two here, so the program knows that this part does not interact with the mold, but interacts with the environment. Click Assign Index, and select index 17 for it again. Done. As we can see, our surfaces changed color, meaning a new index was assigned to them. We return to our simulation settings, and here it's important to understand one thing. In case we don't have a specific volume index for a material, the program will use the index established at the boundary limit. Meaning, if we assign index 1 to this surface, and yet in the parameters of the indices for the mold materials, we don't have any volume with that material, the program will use the boundary limit index. That is, to set the properties of our mold, we have to use the index we assigned for the boundary limits. We assign for our surface index 1. Therefore, here to assign a material for a mold that doesn't actually exist, we have to apply the material for index 1, which matches the established boundary index. Let's select. We said this will be a sand casting. Let it be sand with a binder. Let's say it's a process. Done. What have we done? By starting the work by first assigning the boundary indices, we can, even if we don't have a mold as such with a volume index, by assigning these indices that correspond to the assigned boundary index, we can set the properties of the external part of our mold. There are several things I need to talk about here. Why? Because if we are not using a real volume, we are telling the program that outside this index we have sand. But it's virtual sand, and this will cause various types of errors during the calculation, sometimes important, sometimes not. What am I talking about? For example, if we were using a real mold, the sand here in this area would heat up. And as it heats up, the heating of this part will eventually influence the heating of this part, just as the heating here will influence the heating on the opposite side. If we are using a virtual mold, the program knows that after this boundary here, I have sand, but it's sand that doesn't exist in reality. The program doesn't have a mesh to calculate the temperature development through that mesh. Therefore, the parts will not influence each other. And this can sometimes cause errors in parts where we have sections very close to each other. Actually, the depth of sand heating isn't that great, so the error won't be critical. But you always have to keep in mind that when using a virtual mold, we have these limitations. Really, that's all. We have assigned the material of our mold to our index 1. We have assigned the boundaries for the interaction of our mold with the environment. And what we would need here is, before performing the calculation, to check the quality of our 3D mesh. We can see that this time we do have several errors. There's a triangle that's not quite right here, a triangle with problems here, and one here. Click Correct. The program couldn't correct the triangles. It seems there's some kind of geometry limiting them. In that case, it's okay. We simply delete all the triangles we don't like. Done. The triangles were deleted. We can see we have no more problems in our model. Let's set the parameters of our simulation so we can now perform the calculation. This here is a steel casting. The liquidus temperature, I'll check it here, is 1500 degrees, so I'll set for our simulation, let's say a casting temperature of 1650 degrees. The mold temperature will correspond to the ambient temperature. Let it be 27 degrees. Here also the ambient temperature will be 27 degrees. And we tell the program the number of cores we will use for our calculation. These are the cores of our processor. In my case, it's 4. In your case, you can put either the maximum number of cores or simply dedicate a part of the cores to computation and continue working, doing daily routines without the program fully loading the computer. As we said last time, we cannot use the flow section as it's not available in our free version, and we cannot use any other tabs besides solidification and porosities. In the solidification tab, let's set that yes. We will do the calculation that we want to calculate, that we should save the results for our casting. We can remove the results for our mold, since why save them if we simply don't have them? The calculation step, this part is quite large. The simulation, its solidification will take about an hour. So the calculation step can be left as it is at 1 second. We can put 2. We can make the step smaller, but in that case, the calculation will take longer. We will save the data the same way. With the default parameter, we will save 1 step every 10 seconds to be able to analyze our simulation when the calculation finishes. You always need to check that the option Use Flow Temperatures is deactivated. We also cannot use this option here because it will cause an error. In the free version, we cannot use the flow calculation for our casting. In the Porosities tab, just like last time, we activate the porosity calculation mode and will use the classic porosity formation model simply because it requires no additional adjustments. In the learning class, we are not talking about these parameters. If you are interested in how to set the parameters for the precise porosity model, you can always consult the user guide. It is discussed there very, very precisely. Our simulation is now ready. Let's run it. Click Start Simulation. We save our file with the simulation, and our calculation begins. Again, the program error appears. Could not find a valid license key. It's normal. I repeat that this is normal, as the same program is used for the free license and the commercial license. The only difference is that with the commercial license, you will have many more modules available than we have in the free version. The program switched to the free mode regime, and now our calculation will begin. The calculation will take quite a while, so while it's calculating, let's talk about one more thing. I'll leave this open, close this here. Let's assume our model contains not just one part, but for example, our model was formed from several parts. Meaning, for example, we had exothermic sleeves in this area, in these areas here. Actually, the volumes of the sleeves should have been assigned when we made the 3D model. But for our case, incidentally, I'm going to show you a quite useful tool in the program, which is a tool for partial editing of geometries, directly within the program. I'm going to create volumes for exothermic sleeves to be able to assign properties to them. I switch to the Edit tab. I'm going to select by pressing Ctrl and the left button the surfaces where I will create our sleeves. And here I click the Extrude Our Mesh button. Let's say our sleeves will have a width of 20 millimeters. Click OK. As we can see, the program has created exothermic sleeves on the external part of our model. Just let me see, since we were very close to our mesh, I want to see how many triangles I have set. 494,000. I still have space to do the bottom part. Same as here, we select those surfaces. Excuse me, I hadn't noticed that the calculation ran incorrectly. It seems not. No, everything is correct. I just had the cut view turned on. And at the bottom, I'm going to add a ring using the same tool, just making it a bit thinner. Okay, done. We have managed to obtain 2 additional volumes, one being the sleeve itself, and the other being our ring. What are we going to do now to achieve a correct simulation that contains? I repeat that this part should normally have been done during the creation process of the 3D model. We are doing it here simply to avoid leaving the program. I'll check the number of triangles again. Yes, I'm still within the limit, so I can run this simulation without any problem. What should I do here? First, I switch to our project tree, and I'm going to assign to our volume a volume index that corresponds to the material of our exothermic sleeves. They have index 4. I can see this here, that the volume index being used is index 4. So for index 4, I'll search in our database for some exothermic material. We're talking about a large model, so let it be this one here. Let's see what combustion time it has. If we're talking about an exothermic sleeve with a combustion time of 70 seconds, it could work. The properties of exothermic sleeves are quite complicated. On our website, there's a publication related to the correct use of exothermic sleeves. In this class, we don't have space to talk about this, so we simply select one from the database, and that's it. Since all our volumes are assigned index 4, let's see, this is visible here. As we can see, volume 2 and volume 3 have index 4. Both are made of our exothermic sleeve material. But now what happens? We assign them the volume index, but if I turn off the visibility of our mold's visibility, I can see that the boundary index at the boundary between the exothermic and the model still corresponds to the boundary index established for the casting and the sand. Therefore, when we do this type of work within the program, always remember that we have to go into the boundary index, select the corresponding surfaces, and assign to those surfaces the index corresponding to the material we are using. Assign the volume index. In this case, we are interested in the index corresponding to the casting and an exothermic sleeve, which is index 2. We can now see that the color of this boundary changed here. We also have to do it on the outside to establish the heat exchange parameters between the external part. It seems I selected something extra, but it's not visible. To establish the heat exchange between the external part and our mold, here we assign the index corresponding to the heat exchange between the sleeve and the mold. But one very important thing, we don't have material for the mold. And as I said, if we have an index that interacts with some material, and the material doesn't have its own volume, doesn't have an object it corresponds to, the boundary index number is used for the properties of our material. So for the index we established externally, which this time is the index with the number 3, this one here. We also have to tell the program that outside our exothermic sleeves we have sand, meaning for index 1 we had applied sand, and for index 3 we also have to apply sand. Done. This always needs to be kept in mind, because if we have a real volume, the program will use that volume and the same material will never be repeated in the branch. But since we are using a virtual mold, we need to consider that sometimes, when the interaction is between different volumes with a virtual volume, the parameters will be repeated here in the tree to indicate that this index interacts with sand and the other interacts with sand. And finally, we need to activate the calculation separation button here. This button tells the program that within the elements of our mold, the calculation needs to be done separately. If we don't activate this here, the heat exchange between the external surface and the sand will not work. It's an internal parameter. If we had the real mold, it would have been activated automatically, but since we are working with a virtual mold, we simply activate this button and it will work. Done. Let's run our second calculation. Click. Run our simulation. We review the parameters. We'll leave them the same as last time. Everything here is done. So, we run our calculation. I'll just change the name to have the results under a different name. Here I run a second calculation, and what did I want to talk about here? As we can see, the program, without any problem, even though we have set 4 cores for the first calculation and 4 cores for the second, and today on my computer I only have 4, the program doesn't limit this in any way. We can run calculations in parallel, and they will coordinate among themselves how much computation to use for the first calculation and for the second calculation. The only thing is, since we are doing simulations that last almost an hour, and we are still at second 400, I'm going to stop the recording now and come back when the simulation is finished. I think this will take at least half an hour. See you soon when the calculation is finished. We are back. The calculation of our 2 simulations has finished, so now let's look at our results. I'll close all the windows, and as we did in the previous class, we'll run the Mirage module to view the results. This time I won't go into much detail about the functions of the Mirage module. If you have any doubts, you can watch the previous class. This time, simply to save time, we will analyze the results and see what we have obtained. First, I'll view the solidification of our first simulation, the simulation that did not contain the exothermic sleeves. I select the corresponding file and open it. Here we have the first step of our simulation. I'll set our isotherm to 0% solidification, and let's start the automatic visualization of our solidification. As we can see, our part is solidifying. At a certain point, feeding is lost in this area here, meaning that from this moment on, we can expect shrinkage problems in the area up here. And finally, the process ends. While the simulation visualization is running, open another copy of Mirage to see the obtained porosity results. First, let me turn off automatic playback. And I return to the porosities. I'll go quickly here as I'm not that interested in the dynamics. But anyway, we could also start the visualization to see how our porosities form. But really, in the case of porosity, I'm only interested in the image at the last step of the simulation. Here we can see the result. Although I have the cut view turned on, the result with the isotherm for 1%. If I want to see the surface porosities, I can see I have no surface porosities, but I do have shrinkage defects inside the part, porosities up to 1% in the mentioned areas where we lost feeding, and small porosities in this area down here that was left without feeding in the last step. Let's see why porosity formed here. I return to our solidification, and I'll see what happened. As we can see, in the last step, we have another area that is not fed in this zone. Possibly this could be fixed using some type of chiller, or possibly we could have changed the connection point of this riser. This needs to be investigated more deeply to see what happened in this area here, why this hotspot occurred. What else can we see in our porosities? If I change to higher porosities, for example, say 5%, I can see that the porosities are not that large, and possibly for this type of casting, this design could have been suitable. Again, as I mentioned last time, the quality of our final casting depends on the parameters established by the producer, and we cannot say that any porosity is acceptable or unacceptable. All this depends on the final use of our part. Now let's look at the other simulation we did. The simulation related to the use of exothermic sleeves. Let's open the second file. And we'll see how the solidification behaves for a model that has exothermic sleeves placed on the upper part. As you can see, the temperatures of our risers are maintained by the additional heat applied by the exothermic sleeves. But we still obtain some hot spots here, some unfed zones. Why did this happen? Let's talk a bit about how the virtual mold works and what mistake we made. There was an error here that I made intentionally. What does this error consist of? If we look below our riser, we have a hole, a perforation that normally would not have been made in a real casting, but since we are using a virtual mold, I mentioned earlier that the heat exchange will be from the metal to the sand. But however, the program doesn't know that on the other side, very close, the metal starts again, and therefore this point here acts as an ideal chiller for us. In a real casting, what would have happened is that this area would have heated up immediately. The heat would have been transferred from this side to this side, from this side to this side, and in the end we wouldn't have such a cold spot in this area. But since we are using a virtual mold, we can see that our perforation causes very rapid cooling in this area, which ultimately leads to the loss of feeding, not through the feeding channel, but in the area where the model is providing incorrect data. How to correct these types of errors? There are two ways. First, in the 3D model, when we were designing our CAD, we could have filled this hole here and not left it. The second option could have been to simply draw a very small area here that doesn't contain many polygons of a volume containing sand, and use the virtual mold only starting from this surface, meaning fill the hole with sand in reality. Use real sand here to obtain the heat transfers between the parts, and what is outside, where the heat is truly emitted to infinity outwards, leave that with the virtual mold. I made this error intentionally to explain in a bit more detail the limitations of the virtual mold, and so that you don't make these types of errors in the future. If we look at the result of the porosities, I don't think there will be any difference with the porosity of I'll put them side by side. If we look, here we have an isotherm of 2, here we have one of 1. Let's set it the same, and I'll remove the cut. As we can see, the porosities hardly decreased, for the simple reason that the defects we have in this area are not caused by the loss of feeding, but by an error in the simulation with the use of the virtual mold that we made from the beginning, which prevents us from calculating this area correctly. If we had done it with real sand in this area here, I am more than sure that our riser with exothermic would have worked and we would have obtained a defect-free part. As we can see, inside the riser, the solidification image did change completely. For the area inside the riser, we have a solidification image where you can see the metal remained liquid for quite some time. And for this area, we can see that our solidification occurred almost immediately, which caused porosities inside the part. However, the part that was not with an exothermic sleeve remained completely identical, and the shrinkage defects in the areas where we made no changes should be almost the same. Let me see. Porosity 0.7, here 0.7 as well. Yes, as we can see, our changes and our exothermic sleeves changed the solidification image in the area where we applied them, and all other results remained identical, meaning our simulation worked correctly. With this, I think we will conclude our class dedicated to working in PoligonSoft Free. As you can see, the free version of the program allows us to perform simulations, not just of small things, not just of simple models, but by using the program correctly. We have almost no limitations for the use in case of very complicated models or very large models. What we would do to obtain a simulation in the free program is increase the size of the polygons in our mesh. We would be losing resolution of details in that case, meaning shrinkage cavities, porosities within a polygon, say we have polygons of 20 millimeters, 30 millimeters, won't be visible because the data within a single triangle will always be the same. But the use of the program will allow us to see the solidification dynamics, see the locations of possible defect formations. Therefore, the program can easily be used for many things. Thank you very much for your attention. In the coming weeks, we will possibly be making short videos with details on how to work correctly in PoligonSoft Free. I look forward to your comments. If you have any doubts, you can contact us through all possible channels. Write us an email. Comment below this video. I hope this information has been useful to you and that in the future you will use the PoligonSoft Free program in your work. Thank you very much. See you soon.